And as we did before, we'll click on Julian day. Now, just to do something different, let's go over here to box 25. Box 25 is the smack dab in the middle of the bay, but to do something different, it's the bottom. Okay? Control click, insert, scatter, zap. Okay. And there's a 10-year time series of salinity at the bottom of the bay. Look carefully. So once again, we started the entire Chesapeake Bay, if you will, at 20 parts per thousand salinity, and we're just going to let it crank. And you see that probably this was temperature. It equilibrated in about a year, but soil takes a little bit longer. But 2 years is 730 days. So what you see is for this conservative variable, it takes about 2 years for the bay to equilibrate. If you start with one set of initial conditions and you change something, it's going to take a good 2 years for the bay to really to equilibrate to the new forcing functions. And what we saw here was initial conditions, but you could imagine if you change you change your hydrodynamics. You want to run the model again. You're going to have to run it at least take 2 years for it to equilibrate with salinity. Okay, so there's the message. Okay, let's do another one. I'm kind of catch on to this. Now this time let's do that G1 carbon. So we're going to click on G1 carbon, we're going to open it, and what are we going to do? We're going to go next, next, finish. Everybody's with me? Let's, just for the sake of argument, again we're in the middle of the bay, let's plot that box 5. Okay. Recall, there's a 30-box model. There are 10 columns. So there's one sediment layer under each column in the water. So the sediments go from box 1 at the head of the bay to box 10 at the lower end of the bay, just as the surface water goes from 1 to 10. So we're going to click on J-Day. We're going to click on box 5. Give me the control. Insert. Chart. Okay. So let's look at this one now. A 10-year plot of G1 carbon. This is the labile carbon in the sediments. We started at some uniform value. It goes through a transition, and you know what? In about a year and a half, let's say, depending on how fussy you are, after about a year, certainly within 2 years, the G1 carbon has equilibrated. Again, let's just say for the sake of argument, 2 years, the G1 carbon has equilibrated with an arbitrary initial condition. So, this, all right, fair enough. This just goes on with what, more or less what Dominic showed us yesterday, the G1 is labile. It equilibrates relatively quickly. Now, strictly speaking, how long it took or would take also has something to do with where you started. But if we just start with a number, order of magnitude correct, takes about 2 years. What are we going to do next, John? What are we going to do next? What's that?
Is it you?
You don't win.
G3.
Come on, back up.
G2.
Okay, let's do the G2. And I'll tell you what, let's put this one, I don't know, well, we'll save this for a moment. Let's do the G2. So we're going to go File, Open. It's going to make me go through this long exercise. And we're going to open up the G2 carbon, okay? Next, finish, zap. There's a G2 carbon. Whoa, what are you doing? Come back here. Okay, everybody's set. Let's plot the G2 carbon in box 5. Okay, so what do we see about the G2? What we saw with the G1 was it would take about 2 years to equilibrate from an arbitrary initial condition. Now let's look at the G2. Here's 2 years, 3 years. We're out here, I don't know, at least 7 or 8 years to equilibrate. And this is in keeping with the message that we heard yesterday that the G1 is labile, it goes very quickly. The G2 is refractory, it goes very slowly. So if you want to equilibrate the G2 in the sediments from some arbitrary initial condition, or if you make a change in your inputs, your forcing functions, you've got to run a good 8 or 10 years to equilibrate the G2 sediments with your new forcing functions. All right, now, John, now what do we do?
Sediment or water color?
Sediment.
Sediment. G1, G2. So you look at G3.
Okay. Okay, so let's do the G3. So we'll go File, Open, Computer, Exercise 1, G3. Okay, so we've got the G3. Everybody's with me so far? Whoops, what happened here? What's that?
We need to split the column.
Yeah, it didn't ask me those questions. G3, open. Why didn't it do this before? Next, finish. Okay. So everybody's got to here. So we'll type that. We'll go to box 5. Somebody's ahead of me. All right, that's okay. I'm slow. Yeah, whoa, look at that. It's still going. It's still going. After 10 years, it's still going. Look at that. So if you want to equilibrate to G3, which is effectively inert, very close to inert, you really have to go a long time. Okay, so those are the take-home messages. So we're going to keep going, but keep in mind the water column will equilibrate in about 2 years. The sediments, depending, 10 years or more. So there's a message. I don't know if this next thing is going to work out well or not, but what the heck, let's take a look at the ammonium. Computer, current folder. Let's look at the ammonium in the water column. And we'll open that up. So let's look at ammonium for, I'm just going to tell you, I think I have a feeling. Let's look at about box 23. Let's just see some. What the heck? Let's go to box 23. Box 23 is the bottom layer. near the head of the bay. Okay? And let's see what happens if I do this. Okay, that's not too bad. I'm a little surprised at this, but it's okay. You see that the ammonium probably takes, again, about 2 years. It's not, I'm a little surprised at that, but we'll let that go. The ammonium took about 2 years. You missed an important lesson, Dominic. I showed them that the G1 in the sediment equilibrated in about 2 years, the G2 in about 8 years, and the G3 was still going after 10. It's interesting, I was going to look at the ammonium to see which, in a sense, was more important, the water column or the sediments, because if it was coming out of the sediments, you'd expect to see a trend, because the G2 was still equilibrating up until 8 years. I suspect that is actually here, but in this scale, you just can't see it. The ammonium takes, something on the order of 2 years to roughly equilibrate. I'm surprised. But again, that's what happens when you don't do these things in advance. All right, so let's close all this Excel, and we're going to go back up to the supercomputer. Okay.
Carl, what create the difference between yearly difference, like the yearly difference? What causes that? The numbers. Like year different.
You mean from here to here to here?
After the second year, like it's in equilibrium.
Oh, because the forcing functions change. This is a real bay model. So for example, we have a real meteorological file that changes the temperature, the meteorological forcing every day. So you have winter and summer. So for example, the mineralization in the sediment is temperature dependent. So when it's cold, you don't release a lot of ammonium from the bottom.
But it's just exactly the same time.
Oh, because we're forcing it with exactly the same things. For the real simple case.
So the number is going to be the same.
Yeah.
Exactly the same time of different years.
Right. We have a meteorological file that varies throughout the year, but we use that same file 10 times. We have a boundary conditions file that varies throughout the year, but we use it 10 times. So, and we don't have to do that, but for the sake of teaching, that's a good thing to do, or an easy thing to do. I don't have to make up 10 files. Plus, it allows us to really identify carefully whether what we're seeing is a trend, a time trend, or whether it would be, if I had varying meteorological files, we'd have trouble telling if the changes in G1 or in ammonium were due to time to steady state or whether they were due to a change in the forcing function. So, okay. So I'm going to close out these files. I don't think we're going to need them again.
Carl, Jen has
This one, the peak compared to the G1, like how long is the shifting delay? The peak of the flux of ammonia time and then compared to the G1, that's what we interesting.
Let's see some. So there's our ammonium. Whoa, see it, come back here. What's this? That's G3. Let me put that down for a minute. That's salt. Let me put that down for a minute. There's G1. So it's interesting. You get a peak. We started G1 down here. It went up very rapidly. And what's happening is, the reason it's going up initially is because stuff's settling out of the water. We started the water at some uniform condition and it's settling out. So at least initially the G1 goes up. And then you see that in subsequent years it comes down. So let's look, this is the ammonium. So just as the G1 goes up, you get a peak in ammonium. And goes down, so a second peak, and it settles out to steady state about the third peak, and the ammonium settles out to steady state about the third peak. So actually, you can rationalize, you can see how the ammonium is responding to the G1 in the sediment. Feels good? Move on? Okay. I'm glad you asked that question. If I teach this again, I'll show that, you know. Okay, so I'm going to close most of this out just to get rid of it. I hope I don't hate myself. What else have we got?